And then the last part for finite control volume analysis is related to conservation of energy. Okay, so for the conservation of energy, of course, we need to have that principle. Okay, principle for that conservation of energy. The same goes for conservation of momentum, and similar goes for conservation of mass. Okay, so in conservation of energy, we know that energy in minus energy out equal to delta change of energy. Okay, so this is basic principle for conservation of energy. Okay, so energy for the fluid flow. Okay, so energy due to the pressure, energy due to the energy due to the velocity, okay, due to the movement, due to the dynamic of the fluid, and then energy due to the potential, which is due to the elevation difference. Okay, so this is all the energy that we need to consider. Okay, if our system consists of pump, for example, okay, pump ataupun turbine or any mechanical device, we also need to consider the mechanical energy, okay, produced atau mechanical energy from the pump ataupun compressor and then produced by the turbine. So all this energy need to be considered in our analysis. Okay, so basically for the conservation of energy, we must start the conservation of energy by analyzing the first equation, which is known as Bernoulli equation. Pernah dengar perkataan ni, Bernoulli equation?
Macam
Pernah.
Belajar kat mana?
Fizik.
Oh, fizik. Fizik dah ada Bernoulli equation. Okay, so basically untuk Bernoulli equation, we analyze the pressure energy, we analyze the kinetic energy, and then we also analyze what we call energy due to the potential. Okay, potential energy. Okay, so that is the basic, which is pressure. Pressure ataupun kita panggil dia flow, flow energy. And then apa nama ni, due to the velocity, which is kinetic. And then due to the gravity and also apa nama ni, ketinggian, elevation, the elevation which is known as potential. Potential energy. Okay, so these three energies are the basic energy for fluid flow. Okay, so without any mechanical device such as pump, compressor ataupun turbine, so this is the basic energy for any fluid flow. Okay, so pressure, kinetic energy, and potential energy, and all this energy are described in this Bernoulli equation. Okay, so basically Bernoulli equation it is a very powerful equation, basically in order for the analysis of fluid flow. Okay, so however this Bernoulli equation basically only valid for, okay, so limitation. So this Bernoulli equation, limitation for the Bernoulli equation, number one, it is only for steady. Okay, so what is steady flow? Apa maksud steady flow?
Doesn't change with time.
So delta over delta t equal to 0. So nothing, no variable is changed with the time. Okay, so they was steady. Number two, it only valid for incompressible flow. Okay, so what is incompressible flow? What is constant for incompressible flow? Incompressible, come on. Compressible, incompressible. Density is constant. Okay, so there was incompressible. Okay, and then number three, limitation it is for frictionless flow. Okay, so maknanya apa ni? Frictionless, the viscosity ataupun the friction between the fluid and the body, the friction equal to 0. Okay, so mean that mu equal to 0. Okay, so for this case, for this limitation, number one, steady, incompressible, and frictionless, frictionless flow. Okay, so kalau unsteady, kalau compressible, and then there are viscosity, so maknanya this Bernoulli equation cannot be used. Okay, so ingat so limitation untuk Bernoulli equation steady, incompressible dengan frictionless flow. Okay, so for example, in order to illustrate the limitation in terms of graphical view, so let's say you have this wing, aircraft wing, okay, standard aircraft wing. Okay, and then you free stream passing through this F4. Okay, and then forming this what we call streamline. Okay, so basically for this case, okay, so the steady, incompressible, and frictionless flow only valid outside, okay, only valid outside the boundary layer region. Okay, so valid boundary layer region. So where is the boundary layer region? Kat mana boundary layer region? So boundary layer region is close ataupun very near to the wing ataupun near to the wall. So maknanya kat sini yang merah yang saya buat ni, okay, so the red color, so this is where we describe as boundary layer. Boundary layer region. Okay, so within this boundary layer region, this Bernoulli equation is not valid. Okay, why? Because in this boundary layer region, okay, within this boundary layer region, the flow is basically unsteady, and then the flow is definitely turbulent. Okay, and then flow is there are friction. Okay, so there are friction between the wing ataupun body with the air. Okay, so that's why within this boundary layer region, this Bernoulli equation is not valid. Okay, so you can ingat, this is a simple example in order to illustrate where the limitation of Bernoulli equation. So in that case, for this streamline, okay, so this is streamline. Okay, so for this streamline, the boundary layer, the Bernoulli equation is valid. Sebab apa? Dekat sini, the velocity is almost steady. Memang definitely akan steady, which outside the boundary layer region. The flow is steady, and then incompressible, and then there are no friction. Okay, there are no effect of friction between body and also the streamline. Okay, so that's why in this blue region, the Bernoulli equation is valid. So mean that we can determine the pressure, we can determine the velocity based on Bernoulli equation. Okay, so that is the limitation of Bernoulli equation. Okay, so now let's back to this Bernoulli equation. How to describe the Bernoulli equation? Okay, so Bernoulli equation can be described based on energy. Okay, so macam mana? Bawah sikit. Can be described based on energy, can be described based on pressure, and then can be described based on head. Okay, so head, the unit is length, which is meter. Pressure unit must be pressure unit lah, Pascal ataupun 1 atm bar. So that is pressure, and then energy can be described in terms of kilowatt ataupun kilojoule per kilogram. Okay, so there is the energy, pressure, and head. Okay, so how to describe the Bernoulli equation in terms of energy? Okay, so in terms of energy, P over rho plus V squared over 2, okay, plus Zg equal to constant. Okay, so this is energy equation based on, okay, betul. Okay, so this is Bernoulli equation based on energy. Okay, so meaning that this P over rho, okay, so P over rho, it is flow energy. Okay, so V squared over 2, V squared over 2 ni apa? Ni equation untuk apa? Allah.
Kinetic energy.
Allah, dia ni dia crash. Jap. Okay, dah nampak screen?
Boleh.
Nampak sir.
Okay, so this is apa dia? P over rho saya cakap dia flow energy. V squared over 2. Yang ni kita panggil apa dia? Siapa cakap dia? Kinetic energy. Okay, so maknanya energy due to the velocity for the fluid flow. Zg ni apa? Zg apa? Z multiply with G. Satu lagi energy apa?
Potential.
Potential energy. Okay, so this is equal to constant. Kenapa constant? Kenapa constant? Any idea why it is constant? Ada idea?
Equal energy out.
Yeah, because energy in, very good. Energy in equal to energy out. Sebab based on conservation of principle, ataupun conservation of energy principle, kita tahu energy in tolak energy out equal to delta change of energy. Okay, so since our for the Bernoulli equation, there are no this is only for steady, so nothing change with time, so that's why kita dapat energy in equal to energy out. Okay, so for this case, P1 over rho, sorry, P. Pressure at point 1 over rho tambah dengan V1 squared over 2, velocity at point 1, and then elevation Z1 G equal to P2, pressure at point 2 over rho, velocity at point 2, and then elevation at point 2. Okay, so ni maksud dia Bernoulli equation based on energy equation. Okay, so kita ada flow energy, kita ada kinetic energy, kita ada potential energy. Okay, ada soalan setakat ni?
Sir, yang limitations tu akan jadi our assumptions ke?
Yes, definitely. You have to put all this limitation as your assumption. Okay, so maknanya in order to use the Bernoulli equation, this is your first assumption: steady, incompressible dengan frictionless flow.
Okay.
Boleh?
Boleh.
Okay, so sekarang kita define in terms of energy. So we can define in terms of pressure. Okay, so how to define in terms of pressure? Maknanya P over rho is energy. Kalau pressure P saja kan. So kita kena kali dengan rho. Semua kali dengan rho. So kita akan dapat P plus rho V squared over 2 plus rho G Z sama dengan constant. Okay, so this is how to use Bernoulli equation in terms of pressure. Okay, so P, of course, it is pressure, but what pressure? It is a static pressure. Okay, so nanti next slide saya akan perincikan what is static pressure. Okay, and then the second term, rho V squared over 2, this is pressure due to the velocity, which is known as dynamic pressure. Okay, rho GZ ni apa? Ni dah belajar ni, chapter 2. Rho GZ ataupun rho GH ni pressure apa? Apa? Rho GH tak ingat dah chapter 2?
Fluid.
Fluid apa? Pressure ni pressure apa? Rho GH. P equal to rho GH.
Depth pressure.
Hydrostatic
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 pressure.
pressure.
hydrostatic pressure. Okay, so maknanya kalau based on 2 point P1 plus rho V1 squared over 2 plus rho G Z1 equal to P2 plus rho V2 squared over 2 plus rho G Z2. Okay, so that is for pressure. Define the Bernoulli equation in terms of pressure. So maknanya for the homogeneous dimension, semua ni dalam unit pressure lah. Ni pressure, unit Pascal contoh, Newton per meter square ataupun apa bar, apa-apalah as long as it is unit pressure. So yang ni pun akan unit pressure. This definitely unit pressure. Rho GZ adalah hydrostatic pressure. Apa? Okey. Oh, mati lagi. Flash lagi. One note. Menguji kesabaran manuk ini ya. Okey. Okey, faham Ada soalan setakat ni? Okey?
Okay, sir.
Okay.
Okay, so last
Okay,
kali kita guna how to use pressure atau how to use Bernoulli in terms of head. Okay, so head ni unit length which is meter. Okay, so maknanya macam mana kita nak define the flow energy, potential energy, kinetic energy in terms of head. Okay, so maknanya Z ni kena single Z. So kita kena bahagi dengan rho G. Semua term ni kena bahagi dengan rho G. So kita akan dapat P over rho G V squared over 2G. V squared over 2G plus Z equal to constant. Okay, so this is how to define the Bernoulli equation in terms of head. Okay, so maknanya yang ni nama dia P over rho G, kita panggil dia pressure head. V squared over 2G, kita nama dia velocity head. Okay, Z of course it is head lah, potential. Okay, so of course all the unit must be meter ataupun unit dia adalah unit length. Okay, so for the energy balance, maknanya P1 over rho G V1 squared over 2G plus Z1 equal to P2 over rho G squared over 2G plus Z2. Okay, so this is how to use Bernoulli equation in terms of head, in terms of pressure, and then in terms of energy. Okay, so pressure head, kalau you perasan kita beli, sekejap saya cari specification for pump. Kalau untuk mechanical device, for example pump, so there will be specification. Saya nak suruh nampak macam mana nak relate head dengan pressure head semua tu. Sekejap. Saya Google je. Oh, tak jumpa. Okay, so ni contoh ni je saya jumpa dekat Google. Kalau untuk mechanical device such as pump, compressor, there will be maximum head. Okay, so nampak tak ni maximum head untuk pump ni adalah 22 meter. Ni maximum head. Okay, so this maximum head basically it is calculated based on the pressure head, velocity head dengan potential head. Okay, so kalau you buat total head, okay, total head untuk semua pressure, velocity, potential less than 22 meter, kita boleh gunalah pump ni. Tapi kalau kita calculate total head, pressure, velocity, potential, contoh 30 meter kita dapat. So this pump is not compatible. Okay, maknanya kita tak boleh guna pump ni. Kita kena guna instead of 1 horsepower, kita kena cari 1.5 horsepower for example. Okay, dan inilah yang macam mana kita guna head untuk ataupun dalam mechanical punya device. Okay, biasanya untuk pump, compressor, semua tu akan ada specification based kepada head. Okay, boleh? Ada soalan?
Belum.
Okay, so 10.40 lah. Okay, so tu pengenalan untuk Bernoulli equation. So now let's move to the slide. So ada benda yang saya tak perlu explain lah, you boleh baca sebab saya dah explain dalam first introductory part tadi. So ni pun sama, saya dah explain in term of energy equation. So Bernoulli equation between any two point, okay, any two point on the same streamline. So kita dapat tadi kan, P1 over rho ni apa? P1 over rho apa? This one, P1 over rho. So energy, V square over 2, kinetic energy, is apa? Potential energy. Okay, so sama, you boleh baca ni. Nanti saya dah explain tadi. Potential, flow energy dengan kinetic energy. Okay. And then this is if the flow is unsteady, compressible flow. So but we are not cover up to this unsteady and dengan compressible flow. Okay, so dia sebab apa? Sebab Bernoulli equation hanya untuk steady dengan incompressible flow. Okay, so ni pun saya dah explain tadi. Kita define Bernoulli equation in terms of pressure. Okay, cuma saya P, single P is static pressure. So what is static pressure? Static pressure does not incorporate ataupun does not consider the dynamic effect. Okay, dynamic effect due to the dynamic pressure due to the velocity lah. It represent the actual thermodynamic pressure of the fluid. So this is the same as the pressure used in thermodynamics and property table. So there is the static pressure. Okay, and then rho V squared over 2 ni, which is defined as dynamic pressure. So represent pressure rise when the fluid in motion is brought to a stop isentropically. So there is dynamic pressure. Okay, so pressure due to the velocity ataupun fluid motion. Okay, and then last kali static pressure ataupun hydrostatic pressure. It is not pressure in real sense since its value depends on the different levels, but they depend on depth ataupun depend on Z. It account for elevation effect. For example, fluid weight on pressure. Okay. So total pressure. So what is total pressure? Semualah campur. The sum of static, dynamic and hydrostatic pressure. Sama total head. Okay. Total head. Sum of pressure head, velocity head dengan potential head. Okay. So therefore the Bernoulli equation state that the total pressure along a streamline is constant. Okay. So along a streamline is saya buat yang apa yang saya lukis dekat introduction tadi, yang over the wing, yang blue color tu, dia semua constant. Dia punya total pressure constant along that particular streamline. Okay, so this is very important, which is to define the stagnation pressure. Okay, stagnation is stagnant. Stagnant ni maknanya dia static lah. Kita define when it is when it's brought to the static. Okay, so stagnation pressure, which is the sum of static dengan dynamic pressure. Okay, so it represents the pressure at the point where the fluid is brought to a complete stop isentropic-isentropic. Okay, so how to define the stagnation pressure? So how to define the stagnation pressure based on this apa nama ni? Diagram. Okay, so stagnation pressure can be defined based on this piezometer. What is the function of piezometer? Kita nak cari apa? Nak cari pressure lah, kan? Kita nak cari pressure based on the water level. Okay, and then this is the L shape, which is the pitot tube. Okay, so based on this diagram, we can apply the Bernoulli equation in order to find the stagnation pressure. So what is stagnation pressure? Pressure at static point. Okay, so we can find the stagnation pressure. So stagnant maknanya pressure yang apa nama ni, tak bergerak lah, static, ataupun macam mana kita nak cari that pressure based on the pitot tube. So this is a pitot tube, close up of a pitot-static probe. Okay, so showing the stagnation pressure. This is stagnation pressure hole, and two of the five static circumferential pressure hole. Ni, this is pressure hole. You pernah nampak kat mana ni benda ni? Pitot-static static ni, pitot-static tube ni. Pitot tube pernah nampak tak kat mana-mana? Pernah nampak?
Macam tak.
Macam tak pernah. Awak tak perasan. Dia sekejap saya tunjuk gambar kat mana dia, kat mana dia selalu nampak. Pernah nampak? Kat kapal terbang?
Nampak je.
Pernah.
So yang awak nampak ke depan tu, naik Asia ke, naik Mars ke, whatever airplane lah. Yang tu sebenarnya nak measure pressure and then nak measure velocity based on pressure. Okay, ni yang ni dekat depan, ada dekat sini, ada banyak kapal terbang, ada dekat tepi ni. Okay, so basically tu semua adalah pitot tube. Ni. Okay, so this pitot tube is used in order to measure the velocity. Okay, in order to measure the velocity based on pressure and also based on the altitude. Okay, so pitot tube ni elemen yang sangat penting untuk aircraft sebab dia akan bagi the actual velocity, okay, the actual reading of velocity dekat dalam ni, dekat meter dia. Okay, so kalau you all pernah dengar aircraft crash investigation sebelum MH370 yang paling sekarang ni yang paling legend ataupun yang paling bukan legend, yang paling misteri, the most mysterious airplane crash sekarang ni adalah MH370 sebab tak jumpa kan. Sebelum MH370 yang paling misteri adalah pesawat Airbus, tak salah Airbus France Airlines. Okay, tahun berapa saya tak ingat, tapi dia crash dekat laut Pasifik. Okay, Pacific Ocean. Tak salah saya Pacific Ocean. Dia crash tu sebab apa? Dia setahun daripada dia crash, setahun lepas tu baru jumpa dia punya body airplane semua jumpa setahun selepas dia crash. Okay, and then one of the reason, okay, bukan one of the reason, the main reason kenapa kapal terbang tu crash sebab apa? Sebab pitot tube ni dia tertutup dengan ais. Okay, so you tengok sini stagnation, pitot tube ni dia tertutup dengan ais, penuh dengan ais. Dia lalu sebab kat atas ni kan pressure very low. Okay, so ada ais kat sini. So ada ais, lubang dia tertutup, maknanya dia tak bagi reliable velocity based on pressure, based on altitude. So pilot baca meter, tapi sebenarnya kapal terbang tu tak bergerak ataupun dia punya velocity tu tak sama dengan velocity dekat meter. Okay, so dia stall and then crash. Okay, so yang ni tapi ni selepas je kejadian tu barulah ada satu mekanisme untuk de-ice. Okay, untuk de-ice pitot tube. Maknanya de-icing ni dia punya function dia tak nak bagi ada development ataupun formation of ice dekat pitot tube kapal terbang sekarang, untuk semua kapal terbang. Okay, so yang ni yang saya nak cerita pasal pitot tube. Okay, so maknanya pitot tube ni pun sebenarnya guna Bernoulli equation. Okay, so how to find the stagnation pressure, velocity, ataupun how to find the stagnation pressure. Okay, so let's say this is point 1, this is point 2. Okay, point 2 ni where the stagnation pressure hole is located. Okay, so based on point 1 and point 2, we can apply the Bernoulli equation. P1 over rho V1 square. Rho V1 squared over 2 plus apa ni? Rho G Z1 equal to P2 plus rho V2 squared over 2 plus rho G Z2. Okay, so point 1 and point 2, okay, point 1 dengan point 2 at same elevation. So Z2 dengan Z1 sama. Okay, Z2 sama dengan Z1. So kita boleh cancel out. Okay, so sekarang ni at point 2, at stagnation point, pressure is very high. Okay, velocity ada tak dekat stagnation point? Ada velocity ke tak?
Tak ada.
Tak ada sebab kat sini dia ni you nampak dia just hold, maknanya kat stagnation point velocity equal to 0. Okay, so kita boleh, this is velocity equal to 0. So maknanya in order to read the velocity, we can get based on this piezometer dengan tube ataupun pitot tube, V1 squared rho V1 squared over 2. P2 ni P apa? P2 adalah P stagnant. Betul? So pressure 2 ni adalah stagnation pressure. P2 tolak P1 kali 2 bahagi dengan rho square root. Okay, so this is how to find the velocity based on the pitot tube. Okay, so where P2 adalah P stagnant. Okay, so this equation. Boleh? Faham? Okay, so maknanya velocity, if the velocity is increase, okay, velocity increase, maknanya velocity dekat, the level, pressure level ni akan increase lah. Sebab ni base kepada dia punya pressure different ni, base kepada V squared over 2G ataupun dynamic pressure. Okay, so kalau V increase, maknanya ni pun akan increase. Okay, so this is about the stagnation pressure based on pitot tube. Boleh?
Boleh sir.
Okay, so this is example for pitot tube, static source ataupun pitot static tube. So benda ni nak naik kapal terbang lepas ni, boleh tengoklah benda ni ada dekat kapal terbang air ke Mars ke. Okay, so this is stagnation streamline. Stagnation maknanya kat mana stagnation dia? Kat sinilah. Stagnation point dia. So at here velocity equal V2 equal to 0. Okay, so we can use the Bernoulli equation in order to find the pressure ataupun in order to find the velocity. Okay. Limitation on the use of Bernoulli equation, yang ni saya dah explain tadi. Steady flow, frictionless, no shaft work. Ni maknanya the original equation, the original Bernoulli equation tak boleh ada mechanical device. Contohnya compressor, turbine, pump. Okay. Tapi kalau nak tambah turbine, tambah compressor, tambah pump, yang tu kita kena ada addition, add on. Kita kena add on dekat Bernoulli equation. Still kita guna Bernoulli equation, tapi kita kena add on dia punya power ataupun dia punya pressure daripada pump tu sendiri. Okay, so ni untuk limitation of Bernoulli equation. Okay, so yang ni saya dah explain tadi. Cuma kita boleh define Bernoulli equation in terms of head tadi, pressure head, velocity head dengan elevation ataupun potential head. Okay, so yang ni saya dah explain tadi. So it is often convenient to represent the level of mechanical energy graphically using head height to facilitate visualization of the various term of Bernoulli equation. Okay, so maknanya kita boleh guna hydraulic this term SGL dengan energy grade line based on piezometer reading dengan pitot tube reading. Okay, so now what is hydraulic grade line and then what is energy grade line. Okay, so yang ni tak perlu saya dah explain tadi. Total head, H adalah total head, tambah semua pressure, tambah velocity, tambah elevation ataupun potential head, kita akan dapat H besar, which is total head. Okay, so this is how to define the hydraulic grade line dengan energy grade line. Okay, and then dynamic head. So what is hydraulic grade line? Hydraulic grade line represent the sum of static pressure. This is P over rho, static pressure. P over rho G ni tertinggal. P over rho G and the elevation, sum of the static pressure ataupun pressure head with the elevation head. Static pressure ni pressure head, sebab kita guna head. P over rho G adalah head. Okay, pressure head dengan elevation head. Okay, so this is hydraulic grade line. So where is the hydraulic grade line? So yang ni kita baca base kepada piezometer punya level. Okay, so maknanya kat sini lah. Satu sini, here, and then this here. Okay, so kalau di connect, this dash line, red dash line ni. So this line is known as hydraulic grade line. Okay. So kalau based on pitot tube ataupun level difference in pitot tube, it is known as energy grade line. So energy grade line maknanya kita tambah semua. P over rho G, V squared over 2G and Z. Okay. Pressure head, velocity head dengan potential head. Okay. So yang ni kita baca dekat pitot tube sebut kat atas ni, dekat pitot tube. Okay. So and then in between, difference between hydraulic grade line dengan energy grade line ni, it is depend on the dynamic pressure. Okay, difference between the height of EGL dengan HGL. Okay, so for clear explanation about HGL dengan EGL. Okay, so for stationary bodies such as reservoir ataupun lake, tasik ataupun sungai ataupun tangki, the EGL and HGL coincide with the free surface of the liquid. Okay, so kenapa dia coincide? EGL dengan HGL ni kenapa dia coincide untuk stationary body such as reservoir dengan lakes? Siapa ada idea kenapa dia coincide? Dia satu ni apa nama ni? Dia coincide lah. Siapa ada idea kenapa dia coincide untuk open ataupun reservoir dengan lakes with free surface of the liquid? So apa dia coincide? Ada siapa tahu?
Pressure dia lain.
Right. Sebab apa dia coincide? You tengok balik di sini.
Velocity zero.
Velocity zero. Yes, very good. Velocity zero. Sebab free surface, velocity very low ataupun kita boleh assume velocity zero. So kalau velocity zero maknanya tak ada perbezaan antara HGL dengan EGL. So that's why dia coincide. Dia adalah atas satu line saja. Okay. So ikut boleh. Sebab dia perbeza antara HGL dengan EGL adalah because due to the velocity ataupun due to the V. Okay. The EGL, energy grade line, is always a distance V squared over 2G above the HGL. These two curves approach each other as the velocity decrease and they diverge as the velocity increase. Jadi faham maksud dia? Sebab dia punya distance yang ni antara EGL dengan apa nama ni? HGL V squared over 2G. If V increase, okay, kalau V increase, dia akan diverge. Okay, so kalau V decrease, okay, V decrease, dia akan converge. Okay, so tu maksud dia. Okay, itu maksud EGL dengan HGL base kepada V squared over 2G. Okay, so in an idealized Bernoulli type flow, EGL is horizontal and its head remain constant. Okay, so yang ni kalau idealized. For open channel flow, the HGL coincide with the free surface of the liquid, and then EGL is a distance V squared above the free surface. Okay, so this is for the open channel flow. Okay, so you can read for the pipe exit, what is zero? The pressure head is zero. So HGL coincide with the pipe outlet. Okay, so you can read the example of HGL in EGL. Okay, so based on this apa nama ni definition. Okay, so yang ni dia explain balik tadi. Kalau idealize, kenapa dia jadi straight line, horizontal straight line. Okay, so ni kalau HGL, okay, HGL line, ni HGL, hydraulic grade line, kalau dia intersect dengan fluid, okay, dia intersect dengan fluid, tempat dia intersect tu, okay, kat sini, contoh kat sini dengan kat sini, pressure kat sini equal to 0. Okay, so for hydraulic grade line. Okay, so atas daripada HGL, the pressure is vacuum atau pressure is negative. Bawah HGL, pressure is positive. Okay, so that is hydraulic grade line. Okay, so this is example. Kita cuba buat dua example ni. Okay, so cuba fahamkan dulu. Baca, fahamkan, cuba buat apa nama ni, step by step procedure tu. Kena ada assumption, and then apa ni dia nak, problem statement. Okay, cuba buat dulu. Baca, fahamkan, and then cuba sketch apa yang dia nak, ataupun cuba cari apa yang dia nak.
Tak cuti cikgu cakap.
Tak tahu, ni depan ke? Tu pintu. Okay, so boleh tak ada idea?
No idea, sir.
Idea. Kau lain? Bukan tak ada idea ni, malas nak fikir ni.
Pressure over uji ke sir?
Mana pressure? Dia, awak nak guna pressure. Yang ni dia nak cari head. Nak guna pressure over mana-mana equation untuk Bernoulli equation boleh guna. Cuma apa yang kita nak je membezakan. Kalau nak head, kita guna head lah. Maknanya Z sahaja. Macam tu. Okay, so tengok water is flowing from a garden hose. A child places his thumb to cover most of the hose outlet. Okay, so you tengok kat sini. Dia dah besarkan tu. So maknanya most of the hose outlet been covered by his thumb. Okay, by his thumb. And then causing a thin jet of high speed water emerge. Okay, maknanya yang keluar ni adalah jet velocity ataupun high speed water. The pressure in the hose just upstream of his thumb is 400 kilopascal. Ni kat mana? Upstream.
Atas.
Dekat point 1. So dia dah buat ni. Maknanya pressure in the hose just upstream of his thumb. Okay, so thumb dia kat sini. Just upstream maknanya kat sini lah. Dekat point sini. So that's why you define point 1. So that's why at point 1 pressure equal to 400 kilopascal. Okay, and then if the hose is held upward, okay, what is the maximum head that the jet could achieve? Okay, so maknanya dia nak berapa tinggi ni? Sampai point 2 ni. How much Z1 Z2 minus Z1 ataupun H ni. Dia nak berapa tinggi air boleh dapat dengan 400 kilopascal pressure. Kita boleh guna tak Bernoulli equation?
Boleh.
Okay, tapi nak guna Bernoulli equation, we must come up with the assumption. Okay, satu apa tadi? Steady, incompressible and
Frictionless
flow. Okay, so and then frictionless flow ni termasuklah maknanya friction antara water dengan air ni is negligible. So that's why kita assume it is frictionless. Okay, so dah ada ni assumption ni, barulah kita boleh guna Bernoulli equation. Okay, so macam mana kita nak guna Bernoulli equation? Kita boleh guna P1 over rho G plus V1 squared over 2G plus Z1. Okay, so point 1 kat mana? Point 1 just upstream bawah ni je daripada jari dia. Okay, so this is point 1 ni. This is point 1 and then point 2 kat mana? Point 2 ni dekat maximum level of water can reach. Okay, so there is the point 1 dengan point 2. Okay, so sekarang ni kita kena simplify equation. Okay, sebab daripada apa free body diagram ni, daripada diagram ni kita boleh simplify. Okay, so first one, P1, pressure 1 ada tak?
Ada.
Ada so pressure 1 tak boleh cancel out. Okay, V1 ada tak? V1
Tak.
V1 ni just dekat sini, so dia bagi hint kat sini. V1 squared ataupun V1 is much smaller than Vj ataupun Vz yang keluar ni. So maknanya velocity dekat sini we can assume velocity 1 equal to 0 ataupun kita boleh assume stagnant velocity kat bawah ni but very high pressure. So velocity 1 equal to 0. So kita boleh V1 equal to 0. Okay, so Z1 ni elevation kita punya reference level. Okay, and then P2 pressure tu ada pressure tak P2?
Tak.
Tak ada.
Sebab apa?
Expose.
P2 sebab apa pressure P2 kosong? Kosong sebab exposed to the atmosphere. Okay, so P2. V2
Kosong.
kosong sebab apa?
Berhenti.
Sebab dekat surface ni this is the maximum. So maknanya tak ada velocity dah kat sini. Okay, so that's why velocity is 0. Okay, so Z2 kita carilah. Kita dah simplify, maknanya kita boleh dapatlah Z2 tolak Z1 equal to apa? Z2 equal to P1 over rho G. P1 berapa? 400 kilopascal. Rho ni water water 1000. So dapat apa?
$40.77.
40 ke 14?
40.77.
Meter semua dapat apa ni?
Dapat.
Okay, so maknanya daripada point 1 ni ke point 2 kita dengan pressure almost 400 kilopascal, dia boleh air ni boleh pergi up to 41 meter ataupun 40.77 meter. Okay, faham? How to use the Bernoulli equation? Ada soalan? Okay, so tengok example 5-6 ni. Cuba jawab. Ni pun sama sebab ada elevation different. Kita boleh guna Bernoulli equation. So try guna Bernoulli equation and then cari maximum water velocity at the outlet. Maknanya kat mana tu? Maximum water velocity outlet kat mana? Point 1 ke point 2?
2.
Point 2. Maknanya dia nak V2. So cuba guna Bernoulli equation tapi step by step . Kenapa? Okay, so dapat maximum water V2.
Nine 9.905 ke?
V. Berapa dapat?
9.905.
9 point.
905.
Alright. Siapa lagi dapat? Atau tak buat? Betul atau jawapan 9.9 meter per second. Boleh? So, itulah cara untuk apply Bernoulli equation. Dapat? Ada yang tak dapat?
Yeah.
Okay, so last example. Ni. Velocity measurement by a pitot tube. Okay, so yang ni saya dah tunjuk tadi kan, macam mana nak cari velocity based on pitot tube. Cuba cari ataupun cuba ni nak apa ni? Velocity. Betul lah. Cuba cari velocity V1. Boleh dapat? Dengar tak suara saya? Saya letak mic jauh sikit.
Dengar saya. Belum lagi.
Belum, okey. Semua okey dah masuk minggu depan kita cuti kan?
Ya.
Seminggu. Esok pun cuti. Esok cuti apa? Hari apa esok? Vesak. Vesak day.
Vesak.
So tak ada kelas lah esok.
Minggu depan cuti apa sir?
Minggu depan cuti khas kan? Cuti perayaan lah. Cuti apa ni?
Gawai
Cuti-
keamanan.
Gawai. Cuti khas perayaan. Seminggu. Semua okey so jangan stres-stres. Kita sekarang sedang bergelut dengan COVID-19. Ada pelajar pun ada yang dah kena kuarantin, ada yang dah kena pergi ke MAIX. So stay safe semua. Jangan keluar rumah melainkan apa? Melainkan betul-betul memerlukan. Stay safe dalam rumah je lah semua. Boleh So jangan stres. Kalau stres cari kawan nak berkongsi. Sebab semua orang akan rasa benda tu stres. You all lagi lah belajar, banyak kerja. Nak kena buat, nak kena deliver, nak kena kejar dengan due date. So make sure time management tu sangat penting. So time management berserta dengan stress management. Boleh
InsyaAllah.
Dapat? V1 berapa?
$1.534.
1.53 meter per second. Okay, betul. So V1 equal to 1.53 meter per second. Orang lain dapat tak? So macam mana dapat P1? Macam mana dapat P2?
Rho GH.
Rho GH berdasarkan apa ni? Water level ni kan. P1 ni ni. Point 2 pun sampai level ni. Stagnation pressure. Boleh? So P1 rho GH1 campur H2. P2 equal to rho GH1 campur H2 campur H3. Betul?
Betul.
Okay. So dapat pressure, dapatlah V1 based on Bernoulli equation. Ada soalan? Okay, so for the last part of conservation of energy, so basically conservation of energy related to the first law of thermodynamics, energy in minus energy out equal to delta change of energy in that particular system. Okay, so for any mass system, the net energy supplied to the system equals to the increase of energy of the system plus the energy leaving the system. So basically this description basically related to energy in energy out equal to delta change of energy in that particular system. Okay, so basically you are familiar with this equation because this is the first part of thermodynamics. Okay, first law of thermodynamics that you have learned in this semester. Okay, so that's why thermodynamics and fluid mechanics one is concurrent. Okay, run parallel in one semester sebab dia interrelated antara thermodynamics and also fluid mechanics. Okay, so now for this last part, how do we apply the conservation of energy in the Bernoulli equation? Okay, so in this part, the common part of common equation for Bernoulli is P1 over, if it is defined in terms of head, P1 over rho g plus V1 squared over 2g plus Z1 equal to P2 over rho g plus V2 squared over 2g plus Z2. Okay, so this is Bernoulli equation defined in terms of head. Okay, so this Bernoulli equation is defined based purely on the fluid flow. Okay, so there are no mechanical device. Okay, there are no mechanical device such as a pump ataupun compressor ataupun turbine that produce the work in this particular system. Okay, so in order to include mechanical device, such as pump, compressor, or ataupun and turbine, we need to add on. Okay, we need to include the energy delivered ataupun energy supplied to the system by all this mechanical device. Okay, so mean that this is the equation. So we need to include the mechanical system. So for example, if it is for the pump, if we apply pump, so we need to include HP here for the head pump. Okay, so HP defined as head pump. Okay, so let's say I will give you some simple example. So let's say this is your lake ataupun large reservoir. Okay, and then this is open surface, and then you want to pump this water. Okay, so you want to pump this water to okay, so this is water tank, and then you connect Okay, so this is a simple example. How do we add the mechanical device in order to deliver the water in this system? Okay, so let's say you have this system. This is point 1, and then this is point 2. Okay, both exposed to the free atmosphere. Okay, so by principle, okay, by definition, kalau tangki air ni lagi tinggi daripada water level, okay, so your water level dia tak akan naik secara automatik, okay, dia tak akan naik sendiri, air ni tak akan naik ke water tank, okay, logik ke tak? Dia tak akan naik kalau tak ada pump. So that's why in order to bring the water from this reservoir to the water tank, we need to have what we call pump. Okay, so we need to have pump here. For example, we put the pump here. Okay, so this is pump. So this pump will increase the power, the fluid power ataupun the flow energy, will increase the flow energy, and then the water can be delivered to this water tank. Okay, so mean that if you apply this work in ataupun you apply the energy in to the system, we need to include this energy from the pump. So maknanya equation kita akan jadi P1 over rho G plus V1 squared over 2G plus Z1, and then kita kena masukkan HP. Sebab apa masuk HP dekat sebelah sini? Bukan sebelah P2. Siapa tahu? Kenapa HP duduk sebelah point 1 bukan point 2? Siapa tahu?
Sebab dia tak keluar lagi.
Ya, sebab dia yang tepatnya sebab dia supply energy. Okay. So ingat tak kat sebelah sini energy in, this is energy out. Betul lah tu secara prinsipnya yang cakap tak keluar lagi sebab dia tak keluar tak deliver the energy lagi. So maknanya HP is pump is used to supply the energy. Okay, so that's why it is included in the energy in. Okay, so HP, what is HP? HP adalah head pump. So head unit dia meter. Okay, so this is how to apply the Bernoulli equation by include the mechanical device. For this case is pump. Okay, so it is common. Kalau you nak beli pump, dia akan bagi head. Contohnya dia bagi maximum head 20 meter contoh So this is define the total head based on the Bernoulli equation. Okay, so total head for the pump, for the total head for the pump. Okay, so that is for the this is example, a few simple example for the pump. And then kita ada contoh kita guna turbine. Turbine ni apa function dia turbine?
Generate electric, sir.
Apa?
Generate electric mana?
Tak dengar.
Generate electricity.
Yeah, generate electricity. Maknanya turbine is used to supply the energy to the generator. Maknanya dia duduk kat energy in ke duduk kat energy out?
Another?
Turbine ni dia duduk sebelah energy in ke energy out? Point 1 ke point 2?
Energy in, sir.
Energy in ke?
Energy in. In. Out.
In ke out? Dia supply energy, dia produce energy?
Yeah.
In ke out? In ke out? Tak apa, salah tak apa.
In sir.
In.
Saya rasa in sir.
In Sekejap saya ambil gambar. Saya ambil gambar turbine Sekejap, saya cari gambar sekejap. Gambar yang simple nak faham. Okay, so based on conservation of energy, sama, energy in equal to energy in equal to energy out. Kalau pump, kita guna energy from the pump in order to produce the energy. So maknanya pump is supply the energy. Okay, so energy in. Kalau turbine, dia supply energy ataupun dia produce energy.
Dia produce.
Produce in ke out?
Out.
Out So pump dia duduk sebelah out. Okay. So for example, this is the hydropower plant. Okay, hydropower plant. Hydropower plant maknanya kita perlukan pump tak? Nak turunkan air daripada dam ke generator?
Tak perlu.
Tak perlu. Apa? Sebab kita belajar apa? Kita belajar hydrostatic pressure. Pressure dalam air ni sangat tinggi. Lagi dalam air tu lagi tinggi dia punya pressure, tekanan. Okay, so that's why we don't have to use pump in order to supply the power. Okay, sebab fluid power due to the hydrostatic pressure dah sangat tinggi. Okay, so that's why we don't have to use pump. Okay, so let's say this is point 1 and then this is point 2. Okay, so apply Bernoulli equation. P1 over rho G V1 squared over 2G plus Z1. Ada pump ke tak? Ada HP ke tak untuk case ni? Untuk gambar ni? Head for the pump ada ke tak?
Tak ada sir.
Tak ada sebab kita tak perlu guna pump. So P2 rho G V2 squared over 2G plus mana? Ni point 2 Z2 plus HT. Kat sebelah sini kena ada head for turbine. Sebab apa? Energy is produced from the turbine. So this is head for turbine. And then unit dia adalah meter. Okay, faham? Okay, contoh dia nak increase lagi power daripada daripada fluid flow ni, dia tambah pump kat sini. Contoh. Kat sini dia tambah pump. Okay, so kalau ditambah pump kat sini maknanya kita kena
tambahkan in.
Tambah in ni kena ada HP. Tu je. Add on untuk apa ni? Untuk mechanical device. Boleh faham? Boleh faham? Okay?
Boleh sir.
Okay. So Bernoulli equation ni you kena sentiasa faham. Sebab nanti you dah masuk kerja dengan apa-apalah, kerja dengan GPS ke, kerja dengan JKR ke, you nak design nak design kalau GPS you nak design gate, water gate tu. So semua ni you akan guna Bernoulli equation. Okay, so as a mechanical engineer, Bernoulli equation tu sentiasa ada dalam dalam kepala kita ni. Macam mana nak guna, macam mana kita nak simplify. Okay, so benda ni tak habis kat sini je ni. Bukan habis dekat MSc 441. You akan sentiasa guna selagi you bergelar seorang jurutera mechanical. Boleh? Ingat Bernoulli equation ni makanan untuk pelajar mechanical engineering. Boleh? Okay?
Boleh.
Boleh insyaAllah sir.
Ni kalau ada validity of the equation sama steady flow. all fluid and continuous flow. Untuk ni, untuk yang kita apply tadi. Untuk apa nama ni? Yang ada energy from the mechanical device. So sama saya dah explain tadi. So ni pun sama saya dah explain tadi. You baca nanti. Okay, so dalam energy equation kita apply the kinetic energy correction factor, okay, alpha. So kat mana nak apply alpha? Dekat sini, dekat alpha 1 v squared over 2 g alpha 2 v squared 2 over 2 over 2g. Okay, so what is kinetic energy correction factor? Okay, so the kinetic energy of a fluid stream obtained from v squared over 2 is not the same as the actual kinetic energy of the fluid stream, since the square of sum is not equal to the sum of the square of its component. Okay, so v square ni tak sama dengan, is not equal to the sum of square for its component. Component ni apa? Component x, component y, component z, z direction. So this error can be corrected by replacing the kinetic energy terms v square over 2 in the kinetic energy equation by multiply by the alpha. Okay, so where alpha is the kinetic energy correction factor. Okay, so the correction factor alpha is full is 2 for fully developed laminar pipe flow, and it ranges between 1.04 and 1.11 for fully developed turbulent flow in round pipes. Okay, so ni kalau dia bagi alpha, maknanya you kena simplify, you kena masukkan alpha dekat sini. Kalau dia tak bagi, maknanya you kena letak dalam assumption alpha equal to 1. Okay, so the kinetic energy correction factor are often ignored ataupun is set equal to 1 in an elementary analysis, since most flow accounted in practice are turbulent, for which the correction factor is near unity. Sebab dalam pipe kebanyakannya flow adalah turbulent, ataupun dalam tadi dalam power plant kita tadi pun flow dia tak ada yang laminar sebab very high velocity. So that's why we consider it is a turbulent flow. So turbulent flow correction factor dia adalah 1. So the kinetic energy terms are often small relative to the other terms in the energy equation, and multiplying them by a factor less than 2 does not make much difference. Okay, so that's why kalau untuk turbulent kita set equal to 1. Okay, boleh? Sama macam beta lah. Beta tu apa? Momentum momentum correction factor kan. Beta yang kita guna dalam momentum equation. Okay, so kalau dia tak bagi, kita assume beta equal to 1. Boleh? Okay. Okay, so cuba baca ni. A submersible pump with a shaft power of 5 kilowatt and efficiency of 72% is used to pump water from a lake, from lake point 1 ni, to a pool ke atas ni through a constant diameter pipe. The free surface of the pool is 25 meter above the free surface of the lake. If the irreversible head loss in the piping system is 4 meter, determine the discharge rate of water and the pressure difference across the pump. Maknanya pressure difference ni apa? P2 tolak P2 tolak P1 ataupun P1 tolak P2, sebab P1 lagi tinggi daripada P2. Okay, so cuba you come up with the assumption and then try to come up with the solution. Okay, dapat? Okay, so ada idea? Ada yang dapat jawapan? Dapat? Okay, so maknanya dia ada submersible pump. Submersible pump ni apa?
Pump yang diletak dalam air.
Dia submerge lah. Dia dekat memang dia dekat dalam air. Banyak kita guna submersible pump ni. We have shaft power. Shaft power dia punya shaft power given kilowatt kilowatt is kilojoule per second. So maknanya dia adalah rate of energy. So W dot shaft sama dengan 5 kilowatt. Okay, yang delivered by the pump, and efficiency of 72%. Is used to pump water from a lake to a pool through a constant diameter pipe. So maknanya diameter pipe ni constant. Okay, so diameter pipe sentiasa constant. The free surface of the pool is 25 meter ni. The free surface of the lake is 25 meter above the if the irreversible head loss in the piping system is 4 meter. Okay, so ni apa? Head loss in the piping system. Saya terlupa nak explain tadi. Saya explanation saya akan masukkan dalam ni. So determine the discharge rate of water. So dia nak apa? Dia bagi apa ni? Z2 tolak Z1 25 meter. And then head loss ni berapa? 4 meter. So find discharge rate of water without and pressure difference across the pump ni. Pressure difference tetapi for the pump. Okay, so of course kita kena start dengan assumption lah. Okay, so assumption kita number one steady. Apa lagi assumption dia? This is water, so incompressible. Lagi? So point 1 and point 2 ni boleh buat. Point 1 and point 2 exposed to the atmosphere. Okay, so kita tahu kat sini kalau dia expose to the atmosphere, P1 equal P2 equal to 0 ataupun atmospheric pressure, and then apa lagi yang kosong kalau expose? V1 kosong ke tak? V1 sama dengan V2 sama dengan kosong. Okay, sebab very large and then it is exposed to the atmosphere at point 2 dengan point 1. Okay, so by applying ada pump ke tak? So kita apply Bernoulli equation P1 over rho G plus V1 squared over 2G plus Z1 tambah apa?
HP.
Tambah HP equal to P2 over rho G V2 squared over 2G plus Z2 plus, kena plus apa satu lagi? Ni, head loss. Tambah HL. Okay, so saya nak explain what is head loss. Okay, so head loss ni dia ada dua. Major losses dengan minor losses. Okay, so kat mana ada head loss? Kat dalam pipe. Okay, dalam pipe ni, di constant diameter ni, dalam pipe ni dia ada losses. Losses ni banyak factor. Okay, there are few factor that produce the losses. Okay, so major losses this is due to the leaking, and then minor losses banyak. Minor losses due to the pipe fitting. Okay, pipe fitting ni apa? Kalau ada elbow, kalau ada apa nama ni, losses dekat entrance, losses dekat exit, semua tu kita masukkan dalam head loss. Okay, and then benda ni untuk losses ni saja kita akan belajar chapter 5. Okay, detail untuk losses kita akan belajar losses dalam pipe, kita akan belajar dalam chapter 5. Okay, so tapi sekarang ni dia bagi head loss, so maknanya head loss ni kita apply dekat HL, energy out. Okay, boleh faham? Okay, so P1 boleh potong tak P1?
Tak boleh.
Boleh je.
Ha?
Boleh je.
Boleh
Boleh,
P1 dua-dua exposed to the atmosphere, so P1 sama dengan P2. V1 boleh potong tak? V1 surface ni very low velocity dia sangat small. Okay, so kita assume velocity kosong. V2 pun sama, dia tak tertutup. Kalau dia tertutup lain kalau dia pool ni, contoh pool tertutup rapat, so akan ada gauge pressure dalam ni. So yang tu kita kena berhati-hati. Okay, tapi yang ni exposed to the atmosphere, so dia V2 pun kosong. Okay, so Z1, Z2 ada, and then kita kena cari HP. Sebab apa kita kena cari HP? Sebabnya equation power, okay, power ataupun work for the pump equal to rho G H pump kali dengan V dot. Okay, problem statement kita sekarang ni cari apa? Kita nak cari V dot, betul? V dot ni apa? V dot volume flow rate ataupun discharge. So volume maknanya meter cube per second. Okay, so maknanya kita kena ada HP barulah kita dapat V dot. Tapi W pump, power delivered by the pump ada tak? Dia tak bagi. Tapi dia bagi power delivered to the shaft. Okay, so tak apa. Maknanya kita tahu definition untuk efficiency. Okay, definition untuk efficiency, work work actual. Okay, this is work actual bahagi dengan work actual bahagi dengan work supply ataupun work in. Okay, this is apa nama ni, equation untuk efficiency. Okay, so efficiency untuk pump yang actual dia kat mana? Actual dia maknanya yang delivered, okay, delivered by the pump. Okay, so maknanya kat sini efficiency equal to W dot pump and then W dot shaft. Okay, so efficiency equal to efficiency for the pump work dot pump bahagi dengan W dot shaft. W dot shaft ada tak? W dot shaft ada 5 kW and then efficiency ada. So kita boleh dapat W dot pump. Okay, so W dot pump equal to efficiency for the pump multiply by W dot apa nama ni, shaft. Okay, ni balik, sorry. W dot in, W dot actual. Okay, so maknanya ini yang kita supply, yang ni yang dia keluar, yang dia keluar daripada shaft, daripada pump tu ke shaft, which is W dot actual. Ni dah belajar tak dalam thermodynamics? Dah kan? Efficiency work compressor dengan apa nama ni, turbine. Dah belajar belum? Gas power cycle.
Belum Ustaz.
Belum?
Macam belum.
Macam belum Okay, tak apa. So maknanya lepas ni you boleh terus gunalah dalam thermodynamics. Sepatutnya benda ni you akan belajar dekat thermodynamics lah untuk gas power cycle. Okay, so tapi tak apa, nanti you tu boleh gunalah. Efficiency untuk mechanical device, untuk compressor ke, untuk pump sama dengan work in. Work in ni maknanya work supply daripada electricity tu untuk compressor ataupun untuk pump, and then W actual ni, work actual ni maknanya pump kan dia ada shaft dia kan, yang delivered by the shaft, yang delivered to the shaft. Okay, so yang tu maknanya W dot actual. Okay, so kita dapat pump efficiency dia 72% tak dia, 0.72 kalinya W dot shaft 5 kW. So dapat apa? Sampai 72 kali 5, 3.6 kilowatt. Faham? Boleh? Okey.
Boleh Ustaz. Boleh Ustaz, boleh.
Okey, so cari HP. Cari HP daripada equation ni. Sebab kita nak masuk ni rho G HP. W pump kita dah ada. Kita nak cari V dot. Cari HP. Rearrange equation ni. HP equal to Z2 tolak Z1 tambah HL1. Tambah heat loss. Z2 tolak Z1 berapa? Heat loss berapa?
4.
So head pump 29 meter. So dapatlah V dot. V dot equal to W dot pump bagi dengan rho G HP. Dah bangun baby. Berapa dapat? Widot?
Satu 1.53 tu. 1.53 darah 10 kuasa -2.
1 point
0.0153.
0.0153 meter cube per second.
Volume flow.
Sama Sekejap, saya kira H pump berapa? W dot berapa? W dot pump 3.6 eksponen 3 bahagi dengan 1000 kali 9.81 kali dengan head pump 29. $12.7 kan? 0.0127 kan?
Ya, sir.
Ha?
Betul, sir. Betul.
Ya saya. Saya silap saya.
Betul. 1, 2, 3. 0.0127 meter cube per second. Okay. So inilah dia punya apa nama ni? V dot, volume flow rate. Awak tahu tak volume flow rate ni macam mana? Volume lah. Kalau how you keluarkan apa nama ni? Volume flow rate maknanya dalam satu saat dia boleh deliver 0.0127 meter cube dengan sistem yang kita tengah analyse sekarang ni. Okay, faham?
Faham sir?
Faham, sir.
Faham sir.
So kalau tukar, biasanya kalau you beli pump, dia tak bagi dalam meter cube per second, dia bagi dalam liter. Okay, liter per second. Macam mana nak tukar liter per second? Macam nak tukar liter per... Terkejut saya.
Convert.
Buat macam mana?
1000.
0.0127 meter cube per second. Allah, hilang. Kita tahu 1 meter cube sama dengan 1000
liter.
So 1, 2, 3. 12.7 liter per second. Okay, faham? Ada soalan? Ada soalan untuk chapter 3?
InsyaAllah ada sir.
Tak ada sir.
Okay, so maknanya kita dah tamat untuk control volume analysis. Okay, so control volume kita maknanya kita for the control volume kita ambil volume as our analysis. Okay, so kita dah settle untuk conservation of mass, conservation of energy and also conservation of momentum. Okay, so basically